We'll start today's lecture by discussing node voltage analysis in AC circuits. Okay, last week we solved some examples that we had AC circuits, including AC power supply, uh, resistor, inductor, and capacitor, and we analyzed the circuits by mesh current analysis method. And now I'm going to uh, discuss the analyzing of the circuits by node voltage analysis method. We start by showing some examples. The first example is use node analysis to find Ix. Of course, we all know that how to analyze the circuits, DC circuits by node analysis, and today we will start analyzing AC circuits. We have a voltage source which has a phasor of 75 with the angle of 0. And the circuit is connected to resistors and capacitors and inductors. Okay. Uh, the resistor is 50 ohms. The other resistor also is 50 ohms. This resistor is 60 ohms. The capacitor is negative J 120 ohms, and the inductor is J 200 ohms. Okay, whenever we have a capacitor, definitely the impedance of the capacitor is negative, and if we have an inductor, the impedance of the inductor has to be positive, and the current moving through the inductor is Ix, and we want to find Ix. The first thing we do, we define like a reference point, and then we also identify different nodes. So VA, VB, and VC. Now we write the KCL for these nodes. If we write KCL for these nodes, we will have for node A, we'll start from node A and we say the total of the currents leaving the node are equal to 0. So the total of the currents leaving the node uh, are equal to the total of currents entering the node. So in order to show the currents leaving the node VA, what we do, we say, let's say we have three currents, 1, 2, and 3. Let's call them I1, I2, and I3, for example. So we know that I1 plus I2 plus I3 is equal to 0. Instead of writing I1, we say VA minus VC over 50. So VA minus VC over 50 is I1. The next one here, instead of I2, we write VA minus VB over J200. And finally, instead of I3, we say VA minus 0 over negative J120 is equal to 0. Okay, in fact, we don't need to include these i's in the equations. Instead of these I1, I2, and I3s, we just convert them to the voltage over the resistance by Ohm's law that we just explained in a few minutes ago. So let's just node A. So the current moving from VA to VC, we say it's VA minus VC over 50. The current going from VA to VB is VA minus VB over J20. The current going through VA to the reference point is VA over negative J120 is equal to 0. Node B. The same thing for node B. For node B we say the current going from node B to node A is VB minus VA over J200. The current passing through VB to VC is VB minus VC over 50, and finally the current going from node B to the reference point to the ground is VB over 60 is equal to 0. And node C, in fact for node C we don't need to write any KCL, because in KCL we know that if a node is connected to a voltage source directly, and of course the other side of the voltage source has to be connected to the ground. So if a node is connected to a voltage source directly, we can simply say the voltage of that node is equal to the voltage source. So we don't need to write like any KCL, and we can simply say that VC is equal to 75 with the angle of 0. Now that we reached to this point, we will just factor out voltages, node voltages, VA, VB, and VC, and write equations. But in order to minimize the size of matrices, instead of writing a 3 by 3 matrix, we substitute VC in the other two equations with the value of 75 with the angle of 0. So we will have two equations and two variables because VC is already known. So we will have VA, we factor out VA, 1 over 50 plus 1 over J200 minus 1 over J120 plus VB minus 1 over J200 is equal to 75 with the angle of 0 over 50. First equation. The second equation is VA times negative 1 over J200 plus VB times 1 over 50 plus 1 over 60 plus 1 over J200, which is equal to again 75 with the angle of 0 over 50. Okay, now we put this in the matrix. So in the matrix we will have 1 over 50 plus 1 over J200 plus or minus 1 over J120. We will have negative 1 over J20. We have negative 1 over j, not 20, 200, sorry, 200, and finally 1 over 50 plus 1 over 60 plus 1 over j 200 times VA VB is equal to 75 with the angle of 0 over 50, 75 with the angle of 0 over 50. Of course, we know that 75 angle of 0 over 50 is 75 angle of 0 over 50. So we write the 50 like in the polar form, which is equal to 75 over 50, which is 3 over 2 with the angle of 0 is 1.5. Okay, so we know that we can simplify the matrix in this form, and as a result VA VB is equal to 73.58 with the angle of negative 16.9, and we will have 38.84 with the angle of negative 6.4. Now that we got the voltages in all nodes, we need to find Ix. If we look to Ix, we see that the Ix is the current passing through the inductors. So considering the direction of the Ix, which is from VA to VB, we can say that Ix is equal to VA minus VB over J200. Okay, so we say Ix is equal to VA minus VB over J200, which is equal to 73.58 with the angle of negative 16.9 minus 38.84 with the angle of negative 6.4 over 200 with the angle of 90. We already discussed that J200 converting to the polar form will be the same magnitude with the angle of 90. And then we continue to subtracting these two values and dividing by 200 with the angle of 90. But we know that in order to subtract, I'm sorry, let me just fix it. Okay, in order to subtract the two polar numbers, we need to convert them to rectangular form and then subtract them. Okay, so we need to convert these numbers to polar form, to rectangular form, and then subtract or add them. And if we do that, we will have Ix is equal to 36.1, the angle of negative 28.2 over 20 with the angle of 90, which is equal to 0.18 with the angle of negative 118.2 amp. Okay, so this one is the first example for node voltage analysis.